I guess we're recording. Good morning. I went out to school yesterday and took the measurements for the lab, and I photographed each measurement with my camera, and I'll stitch those together into some kind of a PowerPoint that I can do this afternoon. This week's lab is pretty much filling in a worksheet, making a couple of graphs, I think, and using the slope of the graph to figure out some resistivities of a couple of different types of wire. And just for the sake of completeness, I took one set of measurements with some meters, or a meter that's very much like the one that I had you buy off Amazon, an inexpensive digital multimeter. And then last year I bought a bench top meter, multimeter, and it has the ability to measure resistance much more precisely. Your digital handheld multimeters measure to the nearest tenth of an ohm, and this one measures to the nearest thousandth of an ohm. And so I'm curious to see if we get better values. I know we'll get more precise values of the resistivity with that, but whether it's actually more accurate or not remains to be seen. So we'll see how that happens to work out anyway. Let's see. Any questions on the homework yet? I don't know if anybody's even had a chance to look at it much. We still have quite a bit of material to cover before you'll actually be ready to do that. But today and tomorrow we should be good. Oh, I forgot to put a link up for the OpenStax physics book, but I'll do that. So you could just do a search, and that's basically what the link will say, is just how to do the search for the book and then sign up for an account. And it's got a section. I don't think I ever actually bought a copy of it. I just looked at it online, but it's got a section on motion of charges in uniform electric fields that's I think a bit more thorough than the one that's in your textbook. So I think we're just about ready to switch over here. Pivo visualizer. Maybe I'll just make it screen 2. Okay, and we can minimize that. The one danger of doing this is that I can't see if anybody has a question, so you'll have to speak up if you actually do. Okay. Last couple of days we've been doing a few problems, and we started with just the single particle version of Coulomb's law, which ends up just being the force that one particle exerts on another, and I can call this 1 on 2 if I want to, is going to equal just k q1 q2 over r squared, and that r would be the distance between those two, and we could say that that force is along some vector r12. This, whoops, that's going to be a unit vector that points from particle 1 to particle 2. And so picture-wise, if here's where particle 1 is, and here's where particle 2 is, then along a line connecting 1 and 2, that's where R12 hat is going to point. And so that's what you'd have for a single particle. If you've got a bunch of particles that are exerting a force on another one, the force might look like, I would just call it F, maybe F on 2. And this notation is probably not anything you'd see in the book, but it would look like the sum for I equal 1 to however many particles you have of k q sub I, yeah, let's see. Rather than calling this a 2, I'll just call it the force on a particle. And then Q will be that particle over R sub I squared. And R sub I is going to be the distance. I'll draw a picture to illustrate this. It'll be the distance from the ith particle to particle 2. And then for every one of those things, you'd have to have a different unit vector and R sub I hat. And so that's the way that it's going to look. And this would be picture-wise. Maybe this is our charge Q out here, and then we've got this collection of particles over here, maybe a whole bunch of them, and maybe this is number 1, this is number 2, and this is number n down here. And this would represent R1, it's the distance from particle 1 over there to Q, and this would be R1 hat. And then, let's see, I made that too crowded. I'll do it for the nth particle instead. This would be R sub n hat, and that was R1 hat there. And this would be R sub n. And if any of these particles happen to be a charge opposite that of Q, that'll turn this numerator negative on there, and you'll have this pointing back in that direction. So this formula would take care of all the possible situations. It would be a real pain in the neck to calculate for a large number of particles, which is why we did one example with 2 charges, and that's as far as we're going to go in that direction. But in general, this is what it might happen to look like. Now, instead of a bunch of charges, you might have a continuous charge distribution instead. And in that case, we did one like that yesterday, but it was one-dimensional. In the case of a continuous charge distribution, you take an integral. And the integral would look like kq dq. Let's see, and I need to do something to distinguish these. Maybe I'll call the target charge q sub t. And so I'll draw it out here somewhere. And then we'll have some sort of a charge distribution here that's spread out some way or another. And you'd have to integrate over that thing, all the little dq's, and it would be over r squared. But in this case, r is going to be a variable also. It'll be the distance from some little chunk of charge over here, whoops, missed, to our target particle, and you'd have an r hat. And r hat is going to be something that varies as you integrate over this entire thing. And we'll do an example today where we'll do a 2-dimensional problem where we actually have a direction that's continually changing. And so this can get into a much more serious thing. And the limits of integration are just the place in space where the charge happens to be. It could be a linear charge density, it could be a 2-dimensional area, it could be 3 dimensions. We'll try to stick to 2 dimensions most of the time, although let's see. One of the examples we'll do is kind of a 3-dimensional one, but it's a symmetric situation, so we can argue away one of the variables in there by using that. So that's how it might look for a continuous charge distribution. Now, we're going to extend this idea today, or sort of take a detour from it. And instead of imagining that we have a charge at this point in space, we're just going to imagine this is a point in space, and we'll calculate the force per unit charge that would be on something that was here. So this is a new idea, force per unit charge. But what we would do then is take that force we calculated and divide it by the Q2, pull it out of here, and in this case we'd divide it by the Q, and in this case we'd divide it by the Q sub T, and instead for that point charge we'll just have KQ1 over R squared along R hat, and R hat could point to any place in space. It'll, in this case, it'd be the place in space where Q2 happens to be. But we'll call this the electric field, and we'll use a capital E for that, and the electric field. And it'll be something that exists in space, whether we've got that charge there or not. Last year I watched a series of videos on, let's see, it was about the particle that they discovered at the CERN Large Hadron Collider a couple of years.
Higgs boson, maybe?
Yeah, the Higgs boson. Did you watch that video or not?
Probably at some point.
Okay, well, it's a whole series of them. I think there were either 12 or 24 lectures in it. But Sean Carroll was the person giving it. But he mentioned in there that for particle physicists, there really are no particle physics or particles. There are fields, and at times the field will collapse to form a particle, which is kind of a bizarre idea, but that's the way that it's dealt with mathematically anyway. And so fields are something that we talk about a lot in physics. So we'll just have a particle sitting here, and we'll imagine pick some point in space out here. We'll just call that P, and there would be an electric field. If this is a charged particle and it's not neutral, there'd be an electric field out here that would act on any particle that you happen to put there. And so the R hat in that case is going to point away from the charge. So there's R hat. If the charge that's here happens to be negative, then you'd have the field pointing inward. And so you'd have something like that. The R is the distance from the charge to the field point. And that's something that we'll use a lot. For now, the units of the electric field are going to be, well, this is units of newtons, this is coulombs, and so our units are going to be newtons per coulomb. A little bit later, let's see, the week after next, we'll start dealing with electric potential, and we'll find that an alternative unit for this combination is a volt per meter. And so the stronger the electric field, the higher the number of volts per meter. That's a potential difference between 2 points. And one of the things that's kind of interesting that comes out when you start looking at it from that standpoint is that air has a maximum electric field strength. And what happens is that if you make the electric field too strong, you start pulling the electrons off of the atoms. And if I remember right, it's about 30 million volts per meter, maybe. I may have the number wrong, but it's got a 3 in it, that's for sure. Anyway, if you make the electric field stronger than that, you turn the air into a conductor, and your field collapses for a little while, and you get a spark or a bolt of lightning. And so that's what's going on with those. And so that's the idea of electric field. So this is the electric field for a single charge. For multiple charges, the electric field would look like a sum. So you'll have the sum from I equal 1 to however many charges you have, k q sub I over r sub I squared. And then with each one of those, there would be a unit vector pointing away from the charge to the field point. So we'd have something here. Here's our scattering of charges. And out here is our field point. We don't have to put a charge there anymore. Once we calculate the field, we could stick a charge there. And then the force on that thing is going to equal that amount of charge times E. And in fact, here's something to keep in mind for all of these fields. The force on a particle in an electric field is going to be just the value of the charge times the electric field. So in this case, we've got 1, 2, 3, 4, 5 in here. And with each one of those things, you're going to have a separate distance. And I'll just draw the one for number 4 here. This would be R4 hat, and this would be R4. It'll be the distance from the field point to that fourth charge. So that's the way that the electric field would work for that. And let's see. For a continuous charge distribution, you'll have an integral instead of a sum, and k dq over r squared times r hat. And you have to keep in mind, here we've got 3 variables. You'll have dq, you'll have r, and you'll have r hat. And so that's something that you have to keep track of in all of these problems. And so today I wanted to do just a couple of problems that that would let us do the integration aspect of it. An important thing about the electric field for a point particle is that it points either radially away from the particle or radially inward toward the particle, and it drops off as 1 over r squared. So that's something to keep in mind. It's an important concept for this. One other thing about the electric field, you'll often see sketches that show the electric field. So if you're sketching the electric field of a point particle, if here's your charge there, the way you typically draw the electric field for a positive charge is you'll put, I don't know, it doesn't really matter how many lines you put on it, but you usually try to make a symmetric drawing so it'll have lines pointing out away from it. Sometimes you don't actually connect them to the charge in question, so you'll have an empty space in the middle where you could write Q and put the dot without getting confused. But just in a 2-dimensional sketch here, this is what the electric field for a positive charge would look like. And I know I probably didn't get these quite accurate, but that's what it would look like. And if it was a negative charge, the arrows would all be pointing inward. So you'd stick the arrowhead somewhere in the middle of the thing like that. And electric field sketches are a handy way to get some understanding of what's going on. And I think on the homework assignment, I gave you one where you have a charged particle that's launched into a part of space where you have a uniform electric field between 2 metal plates. And this used to be an integral part of a television set. They did this. If you have a couple of metal plates, and you can have negative charge on this one and positive charge on that one, and the way that you put it onto those things is to hook it up to some sort of a power supply, like a battery sort of, And so you can imagine this, and it's not going to be in the way of the particle that goes in there. So you get a bunch of positive charge on this upper plate, and it will uniformly distribute itself in there. Whoops, minus charge on the top of this plate. And within this region between the two plates, you can have a nice uniform electric field. Next week, we'll do calculations where we show this above an infinite conducting plane. And if you get close enough to a flat plane like this, it'll look infinite. And then you squeeze the distance between these things. But you launch an electron into here, and the electric field gets very weak outside of the region between the two flat plates there. But that's another electric field sketch. And in here, if you remember that F equals QE, well, if your Q happens to be negative, the force is going to be in the direction opposite the electric field. So if the electric field is pointing down here and you launch an electron into it, it'll feel an upward force. And that'll be the direction of its acceleration. And the mathematics that we use to analyze this is the mathematics of projectile motion, because within this region, the electron's going to act like a projectile, except in this case, its acceleration will be upward and not downward like it is for throwing a ball in there. So you have to keep that in mind. But anyway, there's a thing where you might use a sketch. Okay, the problem I wanted to do first here today is one that's very much like what we did yesterday. I used some of the same letters, but I monkey around a little bit with the variables. But if we leave the variables as variables until we get to the calculation point, the math is going to look just like what we did yesterday, so, or very much like it. So here's the situation. We have a charge Q spread uniformly along an insulator, which is a thin rod of length L. That sounds familiar, although yesterday we used a lambda on here. We're to determine, or you are to determine, the electric field at a point P, which is on the axis of the rod, a distance A from the end of the rod as shown in the sketch below. So the sketch looks identical to what we did yesterday, but I did monkey with the dimensions on this thing. Now, the linear charge density of the rod, that's the first calculation we're supposed to do, although I'm not going to use it until we're at the very end. But it's going to look like the total charge divided by the length of the rod. It's supposedly uniformly distributed, and so in this case we'd have 20. In this section of the course, we'll often use these little tiny metric prefixes, like that's the one for micro, so that's 20 times 10 to the minus 6th coulombs. That's what the micro means. And then the length is 0.40 meters. And I've got a note in here, assume two significant figures. So that's something we can do later. But anyway, we'll get coulombs per meter on here. And let's see, 20 divided by 0.4 is about 50, I think. Check that. Times 10 to the minus 6th, or 5 times 10 to the minus 5th. Whoa. I forgot in my class yesterday, I took my calculator out of scientific notation mode to show them numbers that people will often get on their calculators and then write down every one of the digits on here. And I was trying to encourage them to think about significant figures, so they're not doing that all the time. So back to scientific notation mode for me. And then back to not so many crazy significant figures. Okay, 5 times 10 to the minus fifth, or 5.0 times 10 to the minus fifth. Let's see, what are we after here? Oh, that's the linear charge density. Coulombs per meter. Doing this in a weird order. Okay, the electric field in this case, E, is going to look like, well, it'll be an integral of k dq over r squared along r hat. Now, from all of our field elements here through P, our unit vector is going to point in the same direction all the time. And if I let x point in that direction, and then y be perpendicular to it, I can just call our unit vector I hat. And so this thing could be k dq over r squared along, whoops, I hat. Talking and writing at the same time again. All right, now I want to determine an expression for the charge element dq in terms of an integration element dx. So I'll imagine some little thin chunk of this thing that just has a length dx. This is just like what I did yesterday. So we'll have a dx there, and the charge that's on that thing is going to equal lambda dx. So I can say that this is number 1. For number 2, I'll just have dq is going to equal lambda dx. And that's what lambda is. I could rewrite lambda as q over L times dx if I want to, but I'll just leave it that way for now. That's shorter to write than q over L all the time. Let's see, determine an expression for the electric field dE sub x in terms of the line element dx. Okay, this will be the electric field due to some little chunk dq, and so this is dE sub x. I hat's going to be a constant all the way through the integrals, so I don't have to worry about that. But right now, our dE sub x, even if I write dq as lambda dx, I've got a bunch of, or 2 different variables in there. K is a constant. R is going to be the distance from this thing over to here. And if I pick x to be 0 down at this end, this total distance is L plus A. If this is x right here, for that little dx, the distance from dx to here will be the total length minus that length. This is like what we got yesterday. R, and this would be R, and it'll be L plus A minus x. If you add R to x, R plus x will equal L plus A minus x plus x, which is L plus A. And so that does make sense. So working on this thing, this is number 3 that I'm working on now. R is going to equal L plus A minus x. And let's see, I already had dq, it's equal to lambda dx. And so my dE sub x is going to equal k lambda dx over, whoops, L plus A minus x squared. So there's that. That's my expression for the field element. It's just a little chunk of the electric field
due to that little chunk there. And x is going to vary from 0 all the way to L. So when I set up my integral, it's going to look a lot like the expression that we had yesterday. The only thing it's missing is that second charge Q. I'm just after the electric field here instead of the force on some particular charge. So E is going to equal K lambda dx over L plus A minus x squared. And for every one of these, I'm going to have I hat as my unit vector, or every bit of this. So you can pull out the parts. Oh, and I'm integrating from 0 to L. And yesterday I did this exact same integral because the second charge got pulled outside the integral, if I remember right. And it ended up being the integral of dx over L plus A minus x squared. And I did a U substitution. You've seen that calculation. So that's not hugely interesting. But I am going to make it more interesting today. I'm going to take this same situation and move point P off of the axis that I've got here. And we'll see how an integral like that would work out. So this will be a more challenging calculation here, and maybe a more interesting integral, although I bet it's on that sheet of integrals that I showed you yesterday. It's still going to be one of the ones in this set, but we'll see how it happens to turn out. And this will be kind of interesting. So let's draw a picture for this. I'll have my little charged rod here. And I can even use the same letters that I've got here for it. In fact, I can use the same numbers if I want to. And we'll have a point here that is, let this extra distance be A. And then I'm going to toss in, this is the field point, the place I want to calculate the electric field for. And I'll let this distance be D. And just for the heck of it, I'm going to let D equal A, which is 0.25 meters. And I'm not going to plug the numbers in until I get to the very end of this thing. And let's see, I'll use the same L, 0.40 meters. I'll let Q equal 20 microcoulombs. And let's see how this thing is going to work out. So I'll let X equals 0 right here. I'll pick some little charge element here that will be, let's see, dx. Dx wide. The charge on that thing is going to be lambda dx. So my little dq will equal lambda dx, and the distance from that to the origin is going to be x. So, and now the complicated part. I'm going to imagine just going from the center of this. This is supposed to be a thin rod, by the way, so I drew too fat a rod, but here would be my R hat. And I'm going to put a label on here, theta, and I'm going to show you something kind of tricky I can do with this. I can split that R hat into a couple of components, and r hat will equal, let's see, remember r hat is a unit vector, so its hypotenuse is 1, and this side divided by the hypotenuse, which means this side divided by 1 will equal the sine of theta, and this side divided by the hypotenuse, and again the hypotenuse is 1, will equal the cosine of theta. So r hat will actually equal the cosine of theta in the I hat direction plus the sine of theta in the j hat direction. Okay, well that's kind of neat, except theta is going to change continually as we move along this charged rod. So that's something that we'll have to think about. Now our little electric field is going to be dE will equal something I'll have to have. This will be the distance r that's going to matter here. So that's kind of weird. We'll have k dq over r squared along r hat. But now I need to try and zero in on this thing. Well, dq is going to equal lambda dx. So I'll get k lambda dx, and I know lambda is q over L, but I'm not going to worry about it. It's a constant. And then the r down there, oh boy, what's r going to be? Well, let's see. This distance, remember it was L plus a minus x, okay? Or this distance here is L plus a minus x. This is L plus a, this is x, and this is L plus a minus x. So r will equal the square root of L plus a minus x quantity squared plus d squared. So that's good to know geometry-wise. It's, let's see. And that's the Pythagorean theorem, by the way. L plus a minus x is this distance plus d squared, that's a d. That happens to be the length of this hypotenuse. And so I'll have that. Okay. Oh, and then my r hat, which is going to be cos theta along I hat plus sine theta along j hat. Okay, well, I'm making headway. I've got this part of it at least. The only variable left in there is x. I've got dx as my little integration element, and I've got an x that shows up down there. But I've got thetas here, and theta is also a variable. However, the cosine of theta is the side adjacent to the angle divided by the hypotenuse. Okay, well, the side adjacent to the angle, this is that distance L plus a minus x. So cosine of theta is going to equal L plus a minus x divided by r, but r was that thing, which is, oh, this is r squared that's down here. R is the square root. This is r squared, so it's not going to be the square root. But anyway, I'll have L plus a minus x quantity squared plus d squared. And let's see, where else are we going here? I think that's the cosine of theta. And then the sine of theta, that's opposite over hypotenuse. It's going to be d divided by that thing. So it would be d divided by the square root of L plus a minus x quantity squared plus d squared. Okay, well, all we have to do is integrate this, right? So E is going to equal, and this is E as a vector, will equal the integral from 0 to L, because that's where x goes from. I'm integrating over the charge distribution of all this stuff, k lambda dx over the square root of L plus a minus x quantity squared plus d squared. And that's my whole dE. But then I've got this thing in the I hat direction. So I'll have L plus a minus x. Oops, this is squared again, I forgot. And then this is just square root. L plus a minus x quantity squared plus b squared. That's the I hat term. And the j hat term is the sine of theta. So it'll be d divided by the square root of L plus a minus x quantity squared plus d squared. And that's in the j hat direction. Okay. This actually splits it into two integrals. You'll have this one, this times this, and you'll have another integral that's this times this, and that's how you get the result for this. So, I should have done this on a single sheet of paper, but that's okay. I can fold it in half. I may have lost a little bit there, but that's okay. Let's consider the x part of the integral. Whoops, on a blank sheet of paper. And I can just call it E sub x. Okay, E sub x, the x component of the electric field, will be the integral from 0 to L of this term times this term. So I'll have k times lambda times L plus a minus x, and then dx is up there. And what I have on the bottom, this is the square root squared. This is just the square root. Combined, that gives me L plus a minus x quantity squared plus d squared to the 3/2. And so that's what that integral is going to look like. Now, with those L plus a minus x's there, it's kind of a mess. However, I'll use the same u substitution that I did yesterday. I will let u equal L plus a minus x. du is then going to equal minus dx. Maybe there's a more sophisticated way to do this, but I don't know what it is. When x is equal to 0, u is going to equal just L plus a. And when x is equal to L, u will equal a. And so that should be enough to actually change the appearance of this thing. I'm going to pull the k lambda outside. And so I'll have E sub x, because they're constants, is going to equal k lambda. I've got different limits of integration now. I'm going to go from L plus a to a. And I'm just going to have a u on top that's left inside, u du, except it's minus du, so I'll just put a minus sign on that. And there's a way around this. And then in the bottom, I'm just going to have u squared plus d squared to the 3/2. Now, if you do an integral in the reverse direction, you can change the sign of it. So I'll integrate from a to L plus a and just ignore that or get rid of that minus sign. So my e sub x would then become k lambda times the integral from a to L plus a of u du over u squared plus d squared to the 3/2. Now it's not such a scary looking integral, and in fact, this should be one that's on my list here. Let's see, there's one dx over x squared plus a squared to the 3/2. Oh, here's x dx. Here's the tricky part, is recognizing that this integral is the same integral as I've got here. Just change the x's here to u's, and you'll have that one. So this is the form that I want, and it ends up being just minus 1 over u squared plus d squared for my integral. So I will have minus, that's the sign that I get here, minus k lambda times, let's see, 1 over the square root of u squared plus d squared. And making this translation from this form to this form may take a little practice. And I want to evaluate this at a and L plus a. Or, with the minus sign out here, I could do another flip. The negative of this would just be swapping the limits of integration again, but I'm not going to worry about it. So my e sub x, my x component, is going to be minus k lambda times 1 over the square root of L plus a squared plus d squared minus 1 over the square root of a squared plus d squared. And I think that's it. Now, it turns out this is going to be smaller than this, and so I'll get a negative value when I do the subtraction. Or, at this point, I could multiply a minus 1 through here, and I would have k lambda times 1 over the square root of a squared plus d squared minus 1 over the square root of L plus a squared plus d squared. And at this point, we can plug and chug and figure out what e sub x happens to be. So that's not so bad anymore. Well, what about e sub y? What's it going to look like? E sub y will equal, let's see, pull it off over here. I'll have for it k lambda d, and those are all constants, so I can pull them out of the integral. K lambda d times the integral from 0 to L of, let's see, I took care of everything in the numerator. I'll just have a dx on top of this one. And in the bottom, I will have L plus a minus x quantity squared plus d squared to the 3/2. Okay, because I've got it the square root squared here, or the square root to the 2/2, and here's the square root to the 1/2, so I have the 3/2 again. Okay, well, same u substitution, I think. and du is L plus A minus X, or du is minus dx. When X is 0, u is L plus A, u is A, and so this would turn into K lambda D. Again, first step was the integral from L plus A to A. This time I don't have a u in here, I just have minus du, and I'll have u squared, I've got a dying pen, d squared to the 3 halves. Excuse me. Let's see. Yeah, it's practically the same thing, except instead of doing the x dx integral here, I'll just do the dx integral. And so, oh, and I could pull the minus. I'm just going to stick the minus sign out front, I think. E sub y will equal minus k lambda d, the integral from L plus A to A of du over u squared plus d squared to the 3 halves, and just copy it right off there. I will get minus k lambda d divided by, it says divide by a squared. A squared for me is d squared, so I'll have that. And then, let's see, 1 over a squared, I will have u on top and not x, and I'll have the square root of u squared plus d squared. And I'm pretty sure I did that right. And then on the bottom I'll have L plus A and A for the limits. I think I got that right. And let's see what we get for that one. Yeah. Done with the integral table there. By the way, it's kind of amazing that I think every integral we can do this quarter is contained in that set of 1, 2, 3, 4, 5, 6, 7, 8, 9 integrals. So we don't do a whole lot with integration, really. Our geometries are kept pretty simple. Keeping going with e sub y, it will equal minus k lambda d divided by d, let's just call it minus k lambda over d. And evaluating at those limits, for u, I'll have a over the square root of a squared plus d squared minus L plus A over the square root of u squared plus d squared. And if I reverse the order of these two things, I can get rid of that minus sign, and on top I'll have L plus A minus L, or just L. So e sub y will end up being just L, whoops, forgot the k lambda over d part, k lambda over d times L divided by the square root of a squared plus d squared. And so that one's even easier to figure out than the e sub x happened to be. But still, we could plug in the numbers on these things and actually get a value for the electric field. I'm usually more interested in seeing these letter forms of it, because I can kind of imagine, okay, what if we make D huge, like way, way bigger than A, for instance? Okay, in that case, the E sub y would turn into, well, lambda times L would be the total Q on the thing. And this would pretty much just turn into d by itself, because if d squared is way, way bigger than a, then you could just think of this thing inside here as being d, and or d squared. And when you take the square root of that, you just get d. D times d is d squared. I'd have k lambda L, but lambda is q divided by L. So it'd end up being kq over d squared. It would be looking like a point particle. That's the electric field of a point particle. And so that's something that happens. And then you could kind of imagine what happens with E sub x under those circumstances too. All right. Actually, this one ends up going towards 0 if you let d get enormous, I think. So, but that's a problem anyway. So a couple of examples there today of seeing how you could actually integrate and figure out an electric field. Tomorrow, we'll look at the motion of charged particles in electric fields. I think on a schedule I might have put up, we could have spent tomorrow looking at, I think, electric dipoles as well as charges in uniform fields. But I think just doing the charges in uniform fields is okay, because we might look at the electric dipole idea a little bit, but maybe not. Anyway, any questions on that stuff? Fortunately, you'll have a recording of this if you need to go back through and look at how I set up this integral again. This last one was actually a pretty complex situation, but things like that can happen. And I was able to take a complex situation and break it down, eventually getting to fairly simple integrals to do. So that's a skill that it's nice to have if you can take a complex situation and manage to simplify the integral down to something that's not so bad. And it's something that comes with practice. So you may see if you can just duplicate the situation or the calculation that I went through for this, and see how that works. Oh boy. Okay, I'll put together the pictures I took yesterday into some kind of a PowerPoint, and for this week's lab, it'll be filling in a worksheet and making a couple of graphs. So that's all you have to do for it. And let's see if everybody can manage to convert that document into a PDF this week, into a single multi-page PDF. Otherwise, some of you have been doing the things in managing to make everything into a Word document, which is fine. But otherwise, just a PDF. I don't want to get any JPEG files this quarter because I can't edit those and write comments in them. So PDF, that's the key idea, or Word document. So we'll do that. All righty. If there aren't any questions, I'll see you tomorrow. Whoops, I don't want to share the screen. I'm trying to get out of here.